So L'Hopital's rule. Okay, so let f of x and g of x be differentiable functions. Okay, so if, and here it is, if f of a divided by g of a is equal to either 0 over 0 or infinity over infinity, then the limit as x approaches a of f of x over g of x is the same thing as the limit as x approaches a of, and you could just derive the top and derive the bottom, f prime of x over g prime of x. Okay, very, very useful. You'll see. Okay, let's do a few examples on how to apply this. First, we'll start with easy ones, and then if we have time, we'll go to the more complicated ones. So evaluate. Okay, so L'Hopital's rule is just to evaluate limits, and only limits where you have this undetermined form. Okay, so if you have the undetermined form 0 times infinity or 0 power 0 or things like that, you can't use L'Hopital's rule unless you bring it back to this form, and I'm going to show you how to do that also. Okay, so first, let's start with an extremely easy limit. x2 minus 9 over x minus 3. Sorry, not 2, 3 here, sorry. Okay.
But if we know how to do it without using L'Hopital's rule, what's the best way to use it?
Of course.
To do
You could do whatever you want. But now I'm giving you an extra option, and I'm going to use L'Hopital's rule with a very easy example first. And then I'm going to give you one with where you have no choice but to use L'Hopital's rule, or you have no other options. Here, of course, you clearly saw that you could factor and cross out the x minus 3s, and that's how you used to do it, and that's good. Okay. So first thing I do, plug in the 3, and I see that I have 0 over 0, and good. It's one of the 2 undetermined forms, so I'm fine. I could use L'Hopital's rule. Okay, so let's use it. So it's going to be equal to, and I'm going to put a little h here. Okay, and you're going to put a little h for me when you do it on the exam, so that I know that you use L'Hopital's rule. Limit x approaches 3 of what? So the derivative of what is it? Sorry?
f prime of x2 minus 9.
Which is 2x, right? Over the derivative of x minus 1, which is 1. You with me? And then you plug in the 3 inside and you get 6. That's my answer. That's pretty nice. Okay, saves a lot of time. Okay, so I just did the derivative of the top. If you do it the long way, you could do it. I could do it the long way on the side. Okay, so without L'Hopital's rule, so I would do limit x approaches 3, so x minus 3, x plus 3 over x minus 3, cross this out, plug in the 3, you get 6 as well. Okay, remember, that's what we did probably the first day we started calculus, we did such limits. Okay, you with me? Any questions?
Yes, sir, I have a question.
Yes.
How would you know that a function is not differentiable?
Okay, so a function is, we're going to talk about this when we do curve sketching, but for now, these two functions, the top and the bottom, each one is a polynomial, and a polynomial is always differentiable. There's no restriction here involved. Okay, when will there be a restriction? Is if the function has a value of x for which it doesn't exist,
Like square root or
ln,
okay.
or if you had a fraction, if you had x plus 1 over x, for example, x plus 1 over x on the bottom. So of course it can't be 0.
Right, because
Okay,
it can't divide by
so
zero.
not
Okay.
differentiable, exactly. Okay. Number 2. Okay, so try this one. Well, I'll try it. I'll do it with you. So limit x approaches 0 of, so sine x over x. So this we know that it's what?
1.
Yeah, we know that it's 1. Okay, so let's use L'Hopital's rule. So this is, if you plug in 0, you get 0 over 0. So I could use L'Hopital's rule. This is eligible. So limit x approaches 0. So what do I have on top?
Cos x.
Cos x, nice. And on the bottom, 1. Let's plug in cos of 0 is 1. So it's 1 over 1. It's 1. Perfect. You remember how we proved this? We use the squeeze theorem. It took us a page to show that this was 1. Okay, L'Hopital's rule, 1 line. Okay, of course, we will need to prove L'Hopital's rule. That's going to take us more than 1 line. But we'll see if we do it. Okay, try one now. Okay, so let's try to fit one here. So do this one on your own. Limit x approaches 0. So this is going to be a little more complicated, and you try it. So sine x minus x divided by tan x minus x. So first thing I do is, of course, I verify. I plug in 0. So sine 0 minus 0 is 0. Tan 0 minus 0 is 0. So I could use L'Hopital's rule. So equals, I'm just going to move up a bit. Let's see. H for L'Hopital's rule. Limit. Okay, don't forget to write the limit, of course. And the derivative of the top, which is cos x minus 1 over the bottom is secant squared x minus 1. And I replace the 0 inside. I guess cos of 0 is 1 minus 1 is 0. And on the bottom, secant of 0 is 1 minus 1 is 0. I get 0 over 0 again. What do I do?
Yes, it's again.
Oh, I didn't know you could do.
We'll
Could you
repeat.
do
Can we do what? Sorry?
double L'Hopital's rule?
Of course, once I'm here, this is a new limit that I need to evaluate. So I'll do whatever I have, whatever tools I have, whatever resources I use to solve this limit. Okay, I got to
Okay.
here. This is true. Now let's take care of this. So let's do L'Hopital's rule again. Okay, so derivative of, so limit x approaches 0, and then on top I have negative sine x, and on the bottom I have secant squared the derivative, so that's pretty annoying. It's 2 secant x times secant x tan x. Is that okay? The derivative of secant squared and derivative of 1 disappears. Okay, and at this point, I'm going to write here the bottom everything in terms of sine and cos. Limit x approaches 0. So on top, I have negative sine x. And on the bottom, I have 2 times. So secant squared is 1 over cos squared. And tangent is sine over cos. And as you see, the sine x's disappear. And now I can replace by 0. I get negative 1 on top, and on the bottom I get 2 times 1 times 1. So it's 2, so it's negative a half.
Sir, could you re-explain the last step?
the last step, what
The
you
1.5. Before that,
get negative a half.
yes.
I just plugged in 0. So cos of 0 is 1. Cos of 0 is 1.
Okay.
1 times 1 times 2.
Okay.
Okay, another one. Okay, let's do another one. So limit x approaches 0 to sine x minus sine 2x over x minus sine x. First thing we do, we plug in 0 inside, sine 0, sine 0. So I get 0 on top, and on the bottom 0 minus 0 is 0. So I could do L'Hopital's rule. Limit as x approaches 0. And so I have derivative. So I get 2 cos x minus 2 cos 2x. And on the bottom, I have 1 minus cos x. Okay. Plug in 0 again. 2 times 1 minus 2 times 1, I get 0. And on the bottom, 1 minus 1 is 0. Questions? 0 is 0, L'Hopital's rule again. So this will be negative 2 sine x, and then plus 4 sine 2x. And on the bottom, the derivative will be sine x. So I'm going in circle here, circles, because again, I'm going to put 0, 0, 0 again. I'm going to have 0 over 0. So let's do again. Limit x approaches the 0. Derivative of the top, this is negative 2 cos x plus 8 cos 2x. And on the bottom, over cos x. Oh, now I'm out of the woods. Negative 2 plus 8 over 1. So I get 6. That's my answer. Are there any questions on L'Hopital's rule? Another example. So let's say limit x approaches infinity. Let's say 1 plus 2 over x to the power of x. Okay, so here's a pretty complicated limit here. Okay, because if you are to put an infinity here, you will get 1 plus 0, so you get 1 to the power of infinity. Okay, so what's 1 to the power of infinity? Is it 1?
Infinity.
Is infinity? I don't know.
Why wouldn't it be 1?
Okay, exactly. Why wouldn't it be 1? Same thing, 0 power infinity. What would it be? Would it be 0? So 1 power infinity, you have to understand something. If this is a little more than 1, then it's 1.000 something power infinity. So this could go to infinity. Okay, And if you are just a little bit less than 1, let's say you have 0.9999, and you put it to infinity, you could go to 0. Right? If you multiply a fraction by itself, you're going to get to 0. So that's why 1 power infinity is an undetermined form, because of course we're dealing with something that's not exactly 1, it's very close to 1 here. Okay, this is getting close to 1, and this is getting close to infinity. Okay, so there's sort of a race here, and you want to see, so this could either go to infinity, it could go to 0, or it could stabilize somewhere. And you'll see that this one will stabilize somewhere, and let's calculate it. Okay, so of course we cannot use L'Hopital's rule here because we don't have one of the two forms. Okay, so let's do it. Okay, so I wasn't expecting to do it today, but might as well. It's 2 seconds, so it takes 2 minutes. Okay, so I'm going to call this limit, I'm going to call it L. The limit that I'm looking for, let's call it L. 1 plus 2 over x power infinity. That's my limit. Okay, so I hate having a x to the exponent, so I'm going to put ln on each side. So I'm going to put ln here. Where's my ln color? Ln. And so now I have ln of L. Sorry, I forgot to write the limit here. Limit as x approaches infinity. Okay, so ln of L will be the limit as x approaches infinity of the ln of, so n x times the ln of 1 plus 2 over x. You okay with this? I just brought the x in front of the ln.
Wait, if L is limit, why did you add another limit?
No, this one here?
No, first step. What is L?
L is the limit. All this, so all this here, this here like this, I'm calling this L.
Okay.
Okay. The answer to this limit, I'm calling L. Okay, so let me just rewrite it nicely here. So ln of L is equal to the limit as x approaches infinity of, so ln of 1 plus 2 over x times x, or if you prefer, divided by 1 over x, same thing. Okay, so again, if you divide by a fraction, it's like multiplying by x. Let's see what we have here. Plug in infinity here, we have 2 over infinity is 0 plus 1 is 1, ln of 1 is 0. And on the bottom, I have 1 over infinity is 0. Oh, I have 0 over infinity 0 now. Now I could use L'Hopital's rule. Okay, so equals 2. So I'm going to go a bit fast because it's late, and I want to redo more examples of this type on Monday. Okay, but at least you'll have it. Okay, so I'm going to do your L'Hopital's rule here. I'm allowed. And so what's the derivative of ln is 1 over all this, 1 plus 2 over x times the derivative of the inside, which is negative 2 over x2. Okay, so you have to be good at derivatives now. Divided by the derivative of 1 over x, which is negative 1 over x2. Okay, so the negative here and the negative disappear. The x2 disappear. 2 over infinity, this is 0. So basically, I'm left with 2 times 1 over 1. So I'm left with 2. Just 2.
How did we get rid of ln of L?
Sorry?
How did
ln,
we get rid
we won't get rid
of
of it.
ln of?
No, so all this, what we found is the ln of the limit. Understand? So
Okay.
the ln of the limit is 2. So the limit is what? E power 2.
Mhm.
Okay, so the limit of this is e to the power of 2. So like if you take your calculator and you do, let's say, let's put a million here. So 1, so I don't know if you can see what I'm doing, plus 2 divided by a million. I get 1.00002. And I'm going to put this to the power of a million. I get 7.389. Okay, about. Okay, so remember this number, 7.389. Now let's do e power 2. Well, 7.389. Okay, so this, the bigger the x, the closer this value will get to e power 2. That's what it means.
Sir,
Yep.
is it possible to do this without using L'Hopital's rule?
I don't know. Maybe it's possible, but I don't know how. I know if you present me this problem, I'll definitely use L'Hopital's rule. I don't know if there's probably another way. There's always other ways to do it in math, but I didn't think about it too much.